All right.
So right there, stop at 33 and 10.5. Okay. So there's no questions. Last time we got into 10.5, so I kind of wanted to chop the homework a bit. So we got to a certain point. So let's kind of review what we did in 10.5. So the beginning idea of 10.5, and I'm going to show you something kind of cool, and it's okay if you don't agree, because it just is. So 10.5, we talked about complex numbers, and we talked about how to rewrite them in polar coordinates. So if I write this a little bit differently, so I kind of decided to do this. So does anyone remember which axis is the real axis? Yeah, the x-axis sort of becomes a real axis, and then this will be the imaginary axis. If you remember that video I showed you about the lateral, it's kind of nice. So in reality, if I drew an x-axis on the board, the imaginary axis would be coming out. So we just sort of go, wow, and then we make a picture like that. That's not the y-axis, right? If I had an x-axis and a y-axis, the x-axis would have an imaginary axis coming out. So what we do is we just plot that in there. So that's the real and the imaginary. Okay. So what we do here instead is we kind of do like this, just to make it more, what we're used to. So if I want to write this in polar form, actually, let me do this. So if I have a point, x plus iy, how would I get this, the length of this? How would I get the length?
Pythagorean.
Yeah, good. So r squared would equal x squared plus y squared. That was very familiar. How would I get the angle? Good. Inverse tangent of y over x, yes. Okay, so if I'm given a complex number in this form, I could figure these out this way. But another way to kind of think of it is, what is x in polar coordinates? What is x in polar coordinates? R.
Why?
Cosine, because cosine likes x. See, that's why that helps. That helps forever. If you know that cosine likes x, cosine likes y, it's insane the number of things it makes easier to remember. Plus I, so what would y be then?
Sine y.
Sine y. Sine theta. Okay. So I can write a complex number in this form, because if we realize a complex number exists in the real imaginary kind of plane, then to get to it, I can rotate through an angle and I can go out a distance. That's polar coordinates. And one of the unfortunate thing is, I'm going to have to stop short because there's other things we got to get to. But one of the first things, well, the last thing I showed you the other day was if I have two complex numbers, it's 1 and 1, 1 and 1, 1, all ones. And then I get another one, z2 is r2 cosine theta 2, this is a 1, plus I sine theta 2, this is a 1, poor little dude. And I want to multiply those together. I proved this last time, I'm not going to do it again, but if I multiply this together, I'll multiply these together, r1 times r2. And last time I did the whole foiling out, and what it comes out to be is cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. It's kind of crazy. So what that means is, if I took this guy and I raised it to the 5th power, for example. This would just be R1 to the 5th power. R1 times R1 times R1 times R1 times R1. And every time I multiply, I add the angles. So this would be cosine of theta 1 plus theta 1 plus this. So it'd be 5 theta 1s plus I sine of 5 theta 2s. So if I do two different complex numbers, I add their angles inside. If I do the same complex number times itself, I'm going to add the angle to itself. So if I add z1 to the nth power, that would be r to the nth cosine of n theta plus I sine of n theta. Okay, that's kind of insane. So that's the extra bit. That's the bit that comes after number 33. So I just want you guys to know converting a complex number, a complex number into polar form, and then doing some basic multiplication of those. So that's what you're gonna have to do in the homework. So this section, the work is almost exactly the same as the work from like just the straight up polar coordinate section. Finding the angle, finding the r, you just have to put it into this equation. Okay, so let's do it. Yeah.
Where did the I go? Wait, when you move it down?
Sure.
No, the other way down.
Oh, move it up. Okay.
Move it up, I is in front of the sign. Yeah, am I still there?
Yeah. So it's got to be complex, real part plus imaginary part.
No, I was writing down the last part. Just yeah.
All right, let's try problem. Let's see if I get this imaginary number. So that's going to be what quadrant of this weird real imaginary plane would that be in?
Why would
It's gonna be in the
I
second.
didn't say you're wrong, Philip. I'm just waiting to see what everybody else says. Yeah, so 3 minus 4. Yeah, so I'm in the 4th quadrant. Okay. So it'll be 3
Oh, that's-
3 real, 4 imaginary. I'm right there.
okay. I didn't back up.
So what is the r? How do I get the r? So r squared would be,
So we find the length of the triangle or the y value.
stop. Sure, how do I do that?
That's 4i squared.
Stop. No. So how long is this?
3.
3. How long is this?
4.
4. Okay. So it'll be 3 squared plus 4 squared. So it's just x squared plus y squared, right? We know that. We've known that. Yeah.
And the I disappears because it's -1.
Because all I care about is the length. Yeah. The units on this is I. So it's 4 down. So it's the length is 4 on that axis. Yeah.
So the I is not the -1 does not disappear.
The -1?
I being -1.
I squared is -1.
I squared.
Yeah, so we don't put that in there yet. I just want to know the length of this. Yeah.
Okay.
Of course, this one you guys should already know, right? This would be 9 plus 16, 25 squared to 25, 5. So a 3, 4, 5 triangle still works, right? So what we've done is if I call this the real axis and this the imaginary axis, anytime I find a point, I inherently have made a triangle. So everything we've discussed before is immediately exactly the same. I've just found a way to represent a complex number in a XY plane kind of thing. Now I can do all the same stuff we did before. I can see how long that is. I can see the angle that it goes through. I can do all the same stuff. How do I get the angle? How do we get this angle? The tangent theta would equal y over x, so what would that be? 4 over 3, so then theta would be Can somebody do that for me? What do you get? Say again?
This one's radians?
Yeah, radians. Let's use some radians. Sorry, so make sure you're in radians. You're probably still in degrees from the quiz.
Battery is low.
-0.927.
I like it. Is that the right quadrant? Is that angle the right quadrant? If I go negative radians, don't I go this way? Now, how big of an angle is this? If we go all the way to here, how big of an angle is that? If we go all the way to here, what angle is that?
90?
Pi over 2, that's right. And what's pi divided by 2 roughly? Pi is roughly 3. So 3 divided by 2 is 1.5. Did I rotate back to 1.5? No. So am I in the fourth quadrant? Is that angle in the fourth quadrant?
No, it's in the third
Okay, well
one.
now. So if I rotate back roughly negative 1.5, then I'm going to be here.
Yeah, that's in the fourth quadrant.
So did I rotate that far?
Yeah, because that's not.
I did not. Okay, help me. So if I go negative 1.5 back, then I start to get out of the fourth quadrant. Are you guys with me?
Yeah.
Because that is negative 1.5 radians roughly.
Yeah.
I only went negative 0.927, did it? So did I rotate past this? No, so I am in the fourth quadrant. Okay. And so you can always do that. I knew from the beginning that I should be in the fourth quadrant. So when I get my angle, I can just make sure it's in the right place. If it's the wrong place, it's a reference angle, I can just add 180 or something, get it into the right quadrant. Okay. So how do I write? What's the form of the polar form for a complex number? It's r times
R times.
cosine theta plus I sine theta. So now we know everything. We know r is 5 times cosine of negative 0.927 plus I sine of negative 0.927. So just to show you,
Oh, you take the, you also put the theta, oh, it's the same theta.
yeah, we figured out what theta was. We figured out what r was. We just have to plug them in now. Okay. So, just to show you real quick, this isn't going to be perfect. If I do something with this number, why is it not going to come out perfect? Because this number was, is this exactly what that is? We rounded it, correct? But what if I do this? So if I do 5 times cosine of negative 0.927, I should get the real part of this. I get roughly 3, yes? It's not perfectly 3 because we rounded. If I do 5 times sine of negative 0.927, then I should get the imaginary part. Negative 4. It's trying to say negative 4. So you can kind of check your work at the end. Because if I multiply this times this, it's got to be 3. Because that's the real part here, correct? And if I multiply 5 times this, that's got to be negative 4 because that's the imaginary part. These are supposed to be the exact same things, just in different representations. Are you guys with me? Now, here's the real power of this. If I ask you to do 3 minus 4i squared, would that be terribly difficult? What would you do to do this? How do you square anything? You write it.
You put it side by side.
Good, you write it twice. So what if I ask you to do to the 20th power? Do you want to do that by hand?
No.
Or let's do it. You ready? So I'm going to do z to the 20th, right? So this is z. Is that cool? That's what z is, yes? So I'm going to do z to the 20th power. That would be 5 to the 20th power times cosine of 20 times negative 0.927 plus I sine of 20 times negative 0.927. So I just showed you this beautiful shortcut from this fact that I proved yesterday. I want to show you, I have to show you this. Because as a student, I do not blame you if you're like, what the shit? It works back out to this. What good is this, Jeff? You and your math crap can pack it up and leave. No, screw that shit. If I can write a complex number in this form, it is easy as shit to raise it to any power I want to. Do you all agree with me? This would suck. 3 minus 4i times 3 minus... It takes forever just to write the problem. And then you gotta foil, foil, and foil, and then foil, and foil, and foil, and then foil. All right, you guys with me? So instead, I just throw all this shit in the calculator, and I'm done. So I'm going to show you 2 really cool things. There's one. All right, this gets a little crazy, but that's all right. So I'm going to do 5 to the 20th. Jeff, try it again. 5 to the 20th times cosine of 20 times negative 0.927. This is going to be something silly big, but that's okay. Everybody's going to be all right. Everybody's going to be all right. All right. So I get 9.08345, blah, 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 times 10 to the 13th. Is that cool? That's what that means, times 10 to the 13th. So I got the real part. Plus, now if I put in here, and here's something cool, you just hit second enter, go back, and put a frickin' sign in there so you don't have to retype all that shit.
How do you put the sign in there?
Second enter.
Yeah, hit second enter. Oh, I'm sorry. So now it's stuck on the left. So hit second enter. It brings up the last thing you did. Go back and put a sign in there. Plop! So I get plus 2.905, blah, 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 times 10 to the 13th. I. So that is what you would get if you did multiply all that shit out. Now, here's the ultimate thing. Here's the thing you guys, probably none of you knew your calculator could do. Make sure I'm in the right mode. Let me see if I put it there. I can see it better. Bum, 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 bum. Or it doesn't even, oh, there we go. Look down here, real, complex, and then look at that. That's neat, but don't worry about that. We don't know what that means. I don't know if I have to do this, but let's see. Do you guys all see above the dot, the dot? There's an I. You ever notice that? Anybody ever try to do anything with that? So if I put in here, parenthesis, 3 minus 4 second dot to the 20th power. Let's see what it gets. Now why is that not exactly the same?
Because there's no room for it.
No. Why is that number not exactly the same? Is that number? Because 0.927 was rounded. But do you see how that's the same thing? So the calculator's just not rounding? I desperately need you to understand. It's exactly the same thing. We just rounded here, didn't we? That's why it's off a little bit. So that's what you would get if you wrote 23 minus 4i and multiply that shit out until you went past insanity. Okay. You want like there, man. Okay. All right, maybe. So it just takes a little bit to get to a really cool thing. You just have to understand the basics before I can get to a really cool thing. Now here's the other really cool thing. I don't know, you guys want to Sorry?
Is that the final?
Yeah, this is what we got. And it was really close to correct. And I'm cool with it not being correct because we rounded that. If I would have put a negative 0.9 in there, this would have really sucked. I would have rounded way too much. So you don't want to round too much, kids. Okay. So real quick, help me out. If I want to solve this equation, why is Philip wrong? How many answers should there be? You opened yourself up. How many answers should there be to this? We know this, fundamental theorem of algebra. How many answers should there be?
2.
No.
4.
4, that's the power. So the number of answers I get, there could be some repetitions, but the numbers of answers should match the highest degree I see. I should get 4 frickin' answers. So one immediate answer besides 2 is negative 2, because when I raise negative 2 to the 4th power, then negative goes away. It's still freaking 16. There's 2 answers. I'm still missing 2, aren't I?
Yeah.
You're gonna have complex.
I'm gonna have freaking complex. So how do I get that shit? I subtract 16, become a 4. Sort. How do I factor this?
X plus 2, W plus 2.
W squared minus 4. W squared plus 4. How do I factor this?
W minus 2, W plus 2.
How do I factor this?
Now that becomes W.
No, that's a trick question. You can't factor that.
4i.
Yeah, you could. Yeah, no, careful. No. You really can factor this. Let's see if anybody remembers. How do you factor this?
2i.
Good. So what are my 4 answers? Plus or minus 2?
Plus or minus 2i.
Now, real quick, can you guys plot those for me in the complex plane? Do it. Plot those 4 numbers in the complex plane. Do that. So you got the real axis and you got the imaginary axis. Right? So these are going to be simple because each of them only has one part. They don't have real and imaginary.
Oh, I see.
Is that an I at the end? Plus or minus 2i?
That's an I, yep, because they're there. That's the only way this works. Now, the other way to do this, by the way, if you subtract 4, take a square root, doesn't that become
Yeah.
plus or minus 2i?
2i, yeah.
Yeah, that's another way to look at it instead of factoring it like that. So let me do this. So negative 2 is there, 2 is there. Where's 2i and negative 2i?
2i is going up,
2i is up here.
and minus 2i is going down.
Do you see how all the answers, what's the angle here? What's that angle? What's that angle? Good, 90. No trick. What's that angle?
Pi over 2.
All right, so every single one of them are pi over 2 apart, yes?
Yeah. So you can use k.
What was the power again?
20.
What was the power again? 4. So I should get 4 answers, yes?
Yeah.
What's the total angle in a circle? 2 pi.
Yeah.
If I cut that in fourths, don't I get pi over 2?
Yeah.
So, if I have a whatever degree equation equal to 0, I'm going to get that many answers, and they're all going to be equally spaced. How spaced? 2 pi divided by the number of answers. So one more example like this.
Why did you put that 2 pi over there again? Oh, because it's 2 pi the whole thing.
I'm breaking it up into 4 parts because I get 4 answers, and the idea is they're equally spaced, which kicks so much ass. So watch this. How do I solve this?
That would be third space, or degree wise.
Third space. I love it. Final space. No.
So it'd be like 120 degrees apart.
That would be 1.
Yeah, good. So if I do degrees, 360 divided by 3, all the answers should be 120 degrees apart. Where's 120 roughly?
30 degrees past 90.
Yeah, so it's right there. So do you see I'm going to get one real answer? Yes, in fact, you guys all know the real answer. What's the real answer? What do you cube, subtract 27, get 0?
9?
3.
Yeah. That's what
You get one real answer. But if I rotate by 120 degrees, is this going to be a real answer? Here's the real axis, and here's the imaginary axis. Is that going to be a real answer? If it's a real answer, where should it be? Probably on the axis that's called the real axis. Is that going to be a real answer?
No, it's not.
No, it's going to be complex. And then if I go another 120 degrees, is that going to be a real answer? No. And then I go another 120 degrees, and I get back to there.
That'll be a real answer.
That'll be my real answer, then, of course. Then I get all 3 of them.
Wait. So there's 2. The only real answer is sitting at the original point.
The only real answer is this 3.
Gotcha.
So if I do, and just to cut to the chase here, because I don't want to know how many of you have forgotten how to do this, right? Little do, big do, blah, blah, blah. And then if I do quadratic formula here, negative b plus or minus square root of b squared minus 4ac. So it'll be 9 minus 36 is negative 27, I think. Yes. Over 2, I get negative 3 sure, yeah, okay.
Maybe we get that.
Yeah, okay. Negative 3 halves, give or take. Square root of this would be 9 times 3, so it'll be 3i rad 3 over 2. God! If I put that into complex form, it would be 120 degrees over. If I go back 3 halves and up 3 rad 3 over 2, I end up here. It's the same place. Okay, so that's another kind of way to know ahead of time if I'm going to get complex answers. Why wasn't there complex answers for this one? I'm sorry, there's complex, but no real complex. There's purely real, purely imaginary, yes? There is no combination. Why? Because I start at an axis and I rotate 90 degrees. So I always come back to a axis. With 3, I stop short. Oh shit, I'm going to pick up 2 complex, A plus BI kind of answers. A plus BI.
Would that be the same type of concept for everything else? Would that be the same thing for everything else?
Yes. Pretty much, yes. Off the top of my head, yes. Okay. All right. Okay. All right. So in section 10.5, you're not going to do what I just did. This is just me showing you some cool shit. All right. You're going to be doing the basic rewrite a given complex into this form. And then you're going to have a couple we have to multiply to. So you're going to use this idea. All right. So what I want to focus on today is something called parametric. Parametric equations. Has anybody ever seen an Etch-a-Sketch? Anybody not have a clue what the hell an Etch-a-Sketch is? Okay, alright. I'm kind of happy. Let me see if I can find this real quick. If I'm lucky, I can find, let me Google. There's a online, did I spell anything right? Let's see. Oh, I spelled it all. I think this is one of the ones I could use, yeah. So does that look familiar? So if I hit the over arrow, can you see the line starting to go? I don't know if I could, I don't think I could zoom. And of course, Jeff, I was really good. I can make stairs. Ooh, this is stairs. And I'm sitting next to the kid that's making the Mona Lisa. I'm like, what? Shut up. So, do you all agree that the Etch-a-Sketch, what I just drew, is kind of like an XY plane? If I hit one of the 2 buttons, if I rotate one of the buttons, it goes left and right. That's the x-axis. If I rotate the other button, it goes up and down. You guys all with me? With a normal function we've seen, like y equals x squared, doesn't x control what y does? On this Etch-a-Sketch, does x control what y does? I control what both do, correct? Now, I don't show up on the Etch-a-Sketch screen, thankfully, because that would be really weird. So somehow there's an external variable affecting both x and y. So we're so used to x directly affecting what y is going to be. Here, y don't give a shit about x. Y just cares how much I'm turning the knob. So I am the external, we don't call it a variable, we actually call it a parameter. This is why this is parametric equations. So what the shit are you talking about, Jeff? So if I turned one dial a little faster than the other one, wouldn't that go at a different angle? If I turn on both at the same time, do you all agree it would be a diagonal?
Yeah.
Unfortunately, I can't do that on this. It won't, if I put both buttons, it doesn't, it just sits there. But if I do both buttons, it'll go diagonal. If I rotate one of the buttons quicker, it'll go faster up or faster over. Does that make sense? Okay. So, what this means for us algebraically is we're going to have something like this. X is controlled by T, so in this case, I'm T. I'm the T dude. I'm behind the scenes controlling everybody. So let's say X of T is T plus 1, Y of T is 2T plus 3, sure. So I am rotating the Y knob faster. Do you see that? Yeah, maybe. So now the question is, what would that look like? So here's what we do. So normally, if I gave you a function y equals x squared, and we were just learning how to graph it, wouldn't we make an xy table? So here I'm going to do the same thing, except I'm going to make a t
And
X.
is this 10-6 or?
This is 10-6, yes, I think. I don't know sections, I just know stuff. I just drink and know things. So part of the problem has to tell you what t can be. So I'm going to tell you that t is between 0 and 2. So you can think of t as time. As time goes by, y goes twice as fast as x, correct? So again, I'm turning that y knob twice as fast. So it's going to rise faster. Does that make sense? If x was going faster, it would go over faster. It wouldn't rise as quickly. Okay, maybe. I need to buy an actual Etch-a-Sketch. I just need one in my life. I used to have one that sat on my keychain, a little tiny one, and then it got busted. All the stuff came up. Okay, sorry. So t goes from 0 to 2. So what am I going to put in for t to start?
0.
Holy shit. Okay. So if I put a 0 in, what do I get for y?
3.
If I put a 0 in, what do I get for y? I'm sorry, I said y. I meant x. Yeah. So you're right. I get 3 for y. What do I get for x? 1. If I put, now let's leave a little, let's leave a little room. Put 1. Leave a little room. Put 2. So if I put a 1 in, what do I get? 2. 5. Everybody, we're all like, let's let Christina do it. She's doing it. And if I put a 2 in, of course I get 3 and 7. So then to do that, you just plot those points. Now this one's a very basic one. Obviously, it's the first one we're doing. If I make these two functions very different, here they're both linear functions. So the reason I leave space, and I don't really need it for this one because these are very basic, is if I need more resolution. If I start to graph it and it's like jumping around, I'm like, oh, I need to find a point between those two so I can see better how it's moving. Because we could very easily get these funky ass pictures because now y is not tied to x. They're both dependent on t. So I can have something that looks like spaghetti. It just goes, just goes crazy. The reason most of our functions are so perfect, or like they don't go crazy, is because they kind of keep each other in check. Y equals x squared. They can only do certain things. So here, if I graph this won't be very interesting, but it's too bad. And I'll show you why in a minute. So let's say 2, 4, 6, 8. 1, 2, 3. So 0 with this. So here, where are my points here, by the way? What's my point in this first one? Which variable will never show up on this picture? T. So that's like me. I don't show up in the Etch-a-Sketch. So what I normally do for myself is I do this once I finish this TXY table. So I kind of, when I look at it, my eyes go to the right place. So 1, 3, 2, 5, 3, 7. So in this case, I got something pretty boring. Not surprising considering these are very basic equations.
And the slope is different for each one. Or y.
Yeah, exactly. So just to show you, if you have your calculator, hit mode. Do you see right here where it says function? Two things I want to point out. See how it says polar right there?
Yeah.
Real quick, just to show, if I hit polar and I go to y equals, now I got r. So then I can put in then like 3 sine theta, and I can graph it, and I get my, now of course, why does it look like a football? Because the screen is not square.
It's Y and it's sine.
That's why it looks like Stewie laying on his side. So if I hit mode and do parametric,
Looks like Bert.
there you go, yeah. Take parametric, hit y equals, now I've got x of t and y of t. Look, I already had some cool shit in there. Let's see what that looked like. Dude, yeah. So parametric equations, this is a really good example of, sometimes they're used to model comet pathways. So this could be like a comet coming around. They're used to model missiles and such, unfortunately. If I do some trig stuff, like next time I'll show you the butterfly equation. Try this. Nita. That looks like the multiverse goldfish. Okay, as always, I never have enough time. So I'll have the quizzes graded on Monday. Yeah. So this is section 10.6. To be really honest, it's section 10.6 and 10.7 because I think they split up. The graphing is in the next section, which is silly. So you guys can keep on going in the homework.
For the 180 class for the summer, I'm guessing that a test every week based on how many units? It's 5 units. 6
Roughly, yes.
Test every week.
Yes, roughly, yes.
At least a quiz every week. All right.
Yes, exactly.
3 hours of class, 3.5 hours of class a day.
Yeah, I'll send out the homework sheet with the pacing towards the end of this month. You got an email from me, did you?
No, I didn't sign it.
Oh, you haven't signed up yet?
No, because